In this video, we'll cover R's built-in numeric data types. By the end of this video, you should know what the primitive numeric data types are in R, how floating point and integer data types differ from each other, and how imprecision in floating point numbers can cause problems in data analysis. The R code that I show in this video is available on Elms, and you may want to take a minute to download it and open it if you'd like to follow along on your own. So when you're thinking about data types in R, it's important to remember that computers store information in a binary format. This is a sequence of 1 and 0 values. But clearly, computers process many different types of information. Numbers, text, images, audio files, cat videos, basically anything you can think of. So how is it that we convert this abstract information into the binary code that computers use? Computers have a nearly infinite variety of data types or data formats. They provide a clear mapping from a sequence of binary digits back to the information they're supposed to represent. There's a bunch of examples you can see in the real world. IEE 754 is a specification for representing numbers in binary format. Systems like ASCII, UTF-8, or UTF-16 are used to represent text. JPEGs, GIFs, or PNG are used for images, and formats like MP3, ACC, or WAV are used for audio. But basically, any data format that you can think of has some sort of specification that turns that information into the binary sequences that computers are able to process. Each of these myriad formats are called data types. R has built-in support for many different data types, and each has its own purpose. Importantly, R packages can allow R to deal with new data types. When you store information in a variable in R, it stores the binary representation of that data in the computer's memory and the data type. You need both of those to make use of the data, because otherwise it's just a bunch of ones and zeros. The Environment Explorer will not only tell you the content of a variable, but also the data type. So I said that R has its own built-in data types. Each data type has its own specific purpose. There's a few we'll cover today. Those are logical values, which are true-false values. Floating point numbers, which are arbitrary numbers that can have decimal places and exponents. Integer numbers, which are round numbers. Complex numbers, which include the imaginary component. Text, categorical variables, and things we'll cover in future videos, vectors, lists, and other objects. So each of these data types are called primitives because they're built into R and they form the basis of all other data processing. You can determine the type of an R primitive using the type of function. So inside the parentheses in type of, you would put some data that could be a variable or it could just be the actual representation of the data, and R will tell you the data type. You can also tell the data type by looking in the Environment Explorer. R also includes methods for converting between different data types. This process is called coercion. The functions that perform coercion are usually called as-dot functions. So again, there's generally no tidyverse equivalent of these, so they will include a period instead of an underscore. So coercion functions would be things like as-dot-integer, as-dot-logical, and so on. Sometimes data can't be coerced into a new data type. So for example, the word cow can't be converted into a number. If R can't coerce a value, it returns NA. We'll talk about this later because NA is a special value for missing data in R. Importantly, every data type in R can take the NA value. So what are these R data types? We'll start with logicals. Logical values store true-false values. They're the most fundamental unit of information in a computer because you can think of true-false values as being binary, zeros and ones. Our logicals can be true or false. Logical values are generally the outcome of logical tests. We'll talk a little bit about those later, but they may show up in your data for other reasons. Numbers can be coerced into logicals. In these cases, 0 is converted to a false, NA is always converted to NA, and everything else is converted to true. In the reverse, if you're trying to convert a logical into a number, false is always converted to 0, NA is always converted to NA, and true is always converted to 1. Very much in line with the binary logic used in computers, where falses are stored as 0 and trues are stored as 1. Let's look at some logical values in R. So remember that logical values can take 3 possible values, true, false, or NA. These are always represented in all capitals in R. So the true value is true in all capitals. You can see there that typing in true to the console returns the value true. Likewise, typing in false returns the value false. Just to prove to you that R won't take anything, you could try typing in maybe, and you can see that R has no idea what the word maybe means. You can convert numbers to logicals. So trying to convert 0 to a logical will always give you false. Trying to convert 1 to a logical will always give you true. And that's actually the same for any non-zero number. So here, I try and convert 42 to a logical, I get true as well. R will always convert NA to an NA. It's also possible to convert logicals into numbers. True will always be converted to a 1, and false will always be converted to a 0. Floating point numbers are the most common numeric data type in R. They're frequently called doubles, and that's the name that R uses to refer to the data type. They're the default way to store numbers. Floating point numbers are stored in scientific notation. So if you remember, the mantissa in scientific notation is a number with a decimal place and a bunch of stuff after it. And then you have the exponent, which is 10 to some integer power. So an example of scientific notation that we're familiar with is Avogadro's number here, where we have 6.0221409 times 10 to the 23rd power. The mantissa is the front part, and the exponent is the 10 to the 23rd part. There are limits on this method of storing numbers. The mantissa has a fixed number of digits, and so that limits the accuracy of numbers. In modern versions of R, these numbers are accurate to about 16 decimal places. Likewise, there's a limit on how large or small the mantissa can be, which means there's a limit on the largest and smallest possible value that can be stored in a double. This again depends on your computer and the R version, but usually it's around 10 to the 300th power. This also imposes an additional challenge. Floating point operations are inherently imprecise due to rounding, because there's only 16 decimal places of accuracy. We need to think about when this imprecision matters. So as I said, floating point numbers have about 16 significant digits of accuracy. That means if you were conducting financial transactions, there would be penny-level errors in a $10 trillion bank account. This maybe seems like really small errors compared to really large numbers, but this really becomes a problem because mathematical operations, again, are only accurate to 16 digits. So these errors can start to accumulate after thousands or tens of thousands of operations. And this is where it can become a really big deal. Something else to be aware of with all numeric types in R is that there is a maximum and a minimum value that can be stored in those numeric data types. Very large or vanishingly small numbers might overflow. And if that's the case, R has special values to deal with those. They're the INF and negative INF values. You can think of these as infinity. Mathematicians might quibble with me about whether or not they're actually treated like infinity, but whenever a numeric data type is too large or too negative to be stored in a variable, you'll get this infinity or negative infinity instead. Another important difference is that most humans use base 10 to represent numbers. Floating point numbers are represented in binary. There can be subtle differences between these two things. Two numbers that look different by a small amount in binary may look exactly the same in base 10. So this can lead to weird situations where checking to see if two floating point numbers are equal may lead to unexpected results. Floating point numbers can be converted into other data types, and other data types can be converted into floating point numbers. Text data can be converted into a floating point number, but the rules are really complicated, and we'll work through some examples of that. Floating point numbers can also be converted into other numeric data types. Importantly, if you convert a floating point number to an integer, it's going to truncate the decimal part of the number. So it's just going to cut off the decimal point. It's not going to do any rounding. So let's take a look at this in R. By default, all numbers in R are treated as doubles. So if I try and take the number 42 and see what type of data it is, R tells me it's a double. Floating point numbers can be really large. So for example, here I'm going to type in 2 to the 300th power. And you can see that R computes that for me. And that tells me it's a number somewhere around 2 times 10 to the 90th power. Note that when R wants to represent a number in scientific notation, it always uses the E to represent the exponent part of a number. So the way you interpret this number is that it's 2.037036 times 10 to the 90th power. R can also represent numbers very close to 0. So here I'm going to type in 2 to the negative 150th power. R computes the result for me. And again, it writes it out in scientific notation, this time with a negative number in front of the exponent, telling me that this number is very close to 0. So again, floating point numbers only have 16 digits of precision, and this can lead to some weird results. So what I'm typing in here is 1 plus 10 to the negative 20th power minus 1. Now if you did this by hand, the 1s would cancel out, and you would get 10 to the negative 20th power. What you can see here is what R does is it takes 1, adds 10 to the negative 20th power. There's only 16 decimal places of precision, so that 10 to the negative 20th power kind of drops off the end there. Then I subtract off 1, and I get exactly 0 back. So this is how floating point numbers can lead to some very weird results. This can occur in more benign cases as well. So what I have here is I take 1/7, and then I subtract off 1 minus 6/7. Now again, if you did this by hand, 1 minus 6/7 would be 1/7. 1/7 minus 1/7 is 0. What's happening here is R is rounding these numbers in such a way that they aren't precisely equal to each other. And then when I subtract the quantity in parentheses from 1/7, what I wind up with is something that's very, very tiny, but not quite 0. Now you could imagine if you then took this result and then put it in a bin and added it with a bunch of other ones that were slightly imprecise, maybe tens of thousands of times, you'd start to get pretty large rounding errors. And this is what I mean, how errors in floating point calculations can start to accumulate. These tiny numbers, added up tens or thousands of times, can start to lead to very big errors. Remember, there's also 2 special data types for numbers in R, INF and negative INF, which R uses when a numeric data type overflows. So what I'm going to type in here is 10 to the 100th power to the 100th power. That's much bigger than the 10 to the 300th power maximum that R has for storing numbers. And you can see that I get INF as a response. R also gives you INF when you divide by 0. This is maybe different from some other programming languages where this would result in an error. Instead, for example, 5 divided by 0 gives me INF. R can convert text into numbers. So in this example here, I have taken 3.141592654, put it in quotation marks, so R will treat it as text, and I use the add double function to convert it to a number, and you can see I get a number out. R will return NA if it doesn't know how to convert a number. So here, I've just typed the letters PI for pi, and tried to convert those into a number. R returns NA because it doesn't know how to do that. And what you can see from this is that R is really finicky with how it will convert text into numbers. So here, I'll convert 10,000 as text into a number, put it inside quotation marks, and I get 10,000. But if I put a comma in, R doesn't know how to deal with that comma, and trying to convert 10,000 with a comma inside of it gives me an NA. The reason for this being is that different locales on different computer systems might use a comma as the thousands separator or the decimal separator. You need to be explicit about those things when R is converting numbers. And so here, since it doesn't know, it returns an NA instead. So integers are the second most common numeric data type used in R. Integers store whole numbers, so no fractions or decimals. The valid range of integers is much smaller than floats. Typically, the smallest integer is around -2 times 10 to the 9th power, and the largest is around 2 times 10 to the 9th power. You tell R you'd like to store a number as an integer by putting an L after the number. You can also coerce a number to an integer using the as.integer function. So why do we have this second numeric data type? Unlike floats, integers are precise. There's no rounding errors, and tests of equality between numbers always behave as you'd expect. So when is this precision important? First of all, probably in financial transactions. If you want bank accounts to be accurate to pennies or fractions of pennies, you might want to use a precise data type instead of floating point numbers. But also, very importantly, integers are used for identification numbers. So you can think of websites that you might go to where you have a customer identification number. If you have lots of those ID numbers, you don't want customers to get confused with each other because of imprecision. So storing identification numbers as an integer prevents that. Let's take a look at using integers in R. So remember, the default data type for a number in R is a double. So again, if I just type in 42, R is going to give me the number 42, treating it like a double. If I'd like to treat a number like an integer, I need to type an L after it. So here I've typed 42 with an L. R will treat that like an integer. It's important to think about what R will do as it converts other numeric data types into integers. When it does that, R truncates the decimal places in a number. So that means it doesn't round, it just cuts off everything that comes after the decimal place. So here, if I would like to convert pi into an integer, 3.141592654, you see I can get 3. Now that could be the result of rounding. Let's think about the number E, which is 2.71828, and so on. Typing that in, that would normally round up to 3, but as you can see, it truncates it to a 2 instead. And in fact, if I pick a number very, very close to 3, so 2 with as many 9s as I could possibly put after it, I still get a 2. R also has support for complex numbers. These are numbers that take the form of a plus b times I, where a and b are floating point numbers, and I is the square root of -1. We're probably not going to use complex numbers in this class, but you should be aware because it's a built-in data type in R. Now you might think complex numbers are better than floating point, right? They do everything that floating point does, but they also deal with imaginary numbers. There's some big drawbacks to using complex numbers, and I'd avoid using them unless they're necessary. Importantly, they take twice as much memory to store because you have to store both the real and the imaginary part of the number. But on top of that, mathematical operations on computers are substantially slower, even if the imaginary part is 0, because the computer still has to treat it as though it's an operation on a complex number.